In this section, we're going to be going through actual proton NMR spectra, and we'll be looking at the various spectra, and from that and a molecular formula, we're going to deduce organic structures. So let's start with this first example. We're given a molecular formula C7H8O and the proton NMR spectrum. The first thing you want to do anytime you're given a molecular formula is calculate the number of unsaturations. So if you need to review that, you can go back where we did unsaturation calculations and review how to do those. But for this, if you do the calculation, you should find that there's 4 unsaturations. So that means we have some combination of double bonds, rings, or triple bonds to give us our 4 unsaturations. Now from here, I like to typically work my spectrum from left to right. And what I like to do is go through and figure out the different regions that we have. So right here in this 7 to 8 region, if we pull up our table of typical regions, right here in the 6.5 to 8 region, that's the aromatic region. And that's what we have right here. So what we're going to do is, with this being the aromatic region, and we see this integration for 5 hydrogen, that should immediately click that this is a monosubstituted benzene. So we have this multiplet in the aromatic region, and this monosubstituted benzene has 5 hydrogen. Okay, the next thing, we have an integration for 2 hydrogen. Let's make that a CH2. And an integration for 1 hydrogen. Let's make that a CH. Now, use what you have and check it against your formula. 6 carbons here, plus 1 carbon here, plus 1 carbon here. That's 8. Well, based on our formula, we only have 7 carbons to work with. So we've put 1 too many carbons in the spectrum. Also, if we get our hydrogen count, we have 5 hydrogen, 2 hydrogen, 1 hydrogen. That gives us our 8. But we're still missing an oxygen. So, since we have too many carbons accounted for, what if instead of having a CH, we have an OH? And if that's the case, now we have the right number of carbons, hydrogen, and oxygen. Also, our aromatic ring here has 1 ring and 3 double bonds. That's our 4 unsaturations. So that's taken care of. Now we just need to connect these fragments together. And this one should be pretty straightforward. We have our CH2 carbon. That'll connect to the OH. And it'll connect to the aromatic ring because that CH2 needed 2 bonds. The splitting also works out because the CH2 is a singlet and it's bonded to this aromatic carbon that doesn't have any hydrogen and an OH, which is a heteroatom, so you wouldn't expect any splitting. So we can draw this a little more neatly. We have our aromatic ring, CH2, OH, and there's that structure. Okay, our next one, C8H9BRO. First thing, get your unsaturation count, do the calculation. You should find 4 unsaturations. Okay, now we'll work this spectrum. Again, kind of like in our previous example, we have some stuff going on in the aromatic region. But here we have 2 doublets, each integrating for 2 hydrogen. This particular pattern is very indicative of a di-substituted benzene like this, where the substituents are on opposite sides of the ring. The reason for that is we have, call this HA, and HB. And A is a doublet because of B, B is a doublet because of A. So we could have our integration for HB, and HA. So that looks like what we have here, and that also takes care of our 4 unsaturations. But let's work our way through the rest of the spectrum. Down here at 4, we have an integration for 2, so let's make that a CH2, and at 1, a CH3. Okay, now I like to make some notes about what things might be connected to. So if we look at our basic shift table, we see down here in approximately the 2 to 4 region, or 2 to 4.5, and sometimes even a little further, is where we have hydrogen on a carbon next to a halogen or an electronegative atom like oxygen or nitrogen. So what I'm going to do is just make myself a little note here. Telling me that CH2 is connected to an electronegative atom. The CH3 around 1.3, there's nothing too special about its chemical shift. Okay, so now let's see what we've accounted for. We've accounted for 6 carbons, 7 carbons, 8 carbons. So our 8 carbons are good. We've accounted for 4, 5, 6, 7, 8, 9 hydrogen. So our hydrogen count's good. But we don't have our bromine and oxygen accounted for. So that we have them as pieces to use in our structure, let's just write them here on the spectrum. And remember that bromine wants to make 1 bond. Oxygen likes to have 2 bonds. So using that information, let's connect some things together. So now what I'm going to do is think about my splitting. Here we have a triplet. That triplet, n plus 1 is 3. So n must equal 2. That means that CH3 is connected to something with 2 hydrogen. Here I have a quartet. So to get 4 lines, n must equal 3. So that CH2 is connected to something with 3 hydrogens. So it should make sense to connect the CH2 and the CH3. Now you might be tempted, since we wrote the CH2 is connected to an electronegative atom. Well, let's just connect it to the bromine. Well, if you do that, we just connected all of our bonds and made bromoethane, and there's no way to connect the rest of the stuff, so that doesn't work. So it's going to be better to connect that to the oxygen. Then we can connect the oxygen to one side of the aromatic ring, the bromine to the other side. And now everything's connected together. Okay, let's redraw this structure a little more neatly. Here's our aromatic ring, our bromine, and then we have an O, CH2, CH3. Okay, in example 3 we have C5H10O2. Should find that there's one unsaturation in that formula, so that means we either have a double bond or a ring in this structure. Okay, so first let's just go through and assign fragments to each peak in the spectrum. So I'm going to do a CH, CH2, CH, and then we can't have CH6. So down here in this region, we probably just have two CH3 groups that are equivalent. Okay, so that takes care of our 5 carbons and our 10 hydrogen, but we still have 2 oxygens unaccounted for. But if we think about the different regions in our spectrum, what tends to show up down here near 10 parts per million? Let's look at our shift table again. And in that 9 to 10.5 region, that tends to be aldehydes, and then in more the 11 to 12 region tends to be carboxylic acids. So here we're not quite at 10, so this falls in the region for an aldehyde. Also, the fact that it's a triplet means they're splitting. You'll get splitting in aldehydes, but if we had a carboxylic acid like this, there's no coupling through this heteroatom, that would just be a singlet. So it's not that. So let's make this an aldehyde. Now one thing I am going to do, I want to go ahead and cross out this CH since it's represented right here. We don't want that fragment written twice, otherwise you might get confused and try to connect both of them. So now we've taken care of one of our oxygens. So there's one other oxygen in the structure we need to use. I'm also just going to make a couple of notes and say that this CH2 and this CH, that's in the electronegative region. That means there's likely some electronegative atom connected to the carbons. Okay, with all of this in mind, let's try to connect some things together. Well, the CH3 groups, those show up as a doublet. Well, n plus 1 equals 2, a doublet. So n must equal 1. So they're connected to a CH. Well, there's only one CH in this spectrum that we can connect those to, and that's the CH right here. So let's go ahead and make that connection. Okay. Now, the CH is a septet. That's 7. So N equals 6, and we've already taken care of the connection to carbons with a total of 6 hydrogen. So that can't be connected to any other CH carbons. But we actually want to make a connection to an electronegative atom because of our note. And what do we have? We have this oxygen that wants to make 2 bonds. So let's connect that. Well, we can give the oxygen its second bond by connecting it to this CH2. And then all that's left that needs connection, we have the aldehyde carbon and this CH2 carbon that only has 3 bonds right now. Let's connect those together, like that. And that explains why the aldehyde here is a triplet, because N equals 2, so it's connected to this carbon with 2 hydrogen. This CH2 is a doublet, because it's connected to a carbon with 1 hydrogen. So the 1 plus 1 is 2, giving you the doublet. Okay, so let's clean our mess up here a little bit. Start with our aldehyde. We have our CH2, O, CH, and our 2 equivalent CH3 groups on that carbon. So that's the structure represented by this spectrum. And also our one unsaturation is this carbon-oxygen double bond. So we've taken care of that. Okay, so here we have C3H9N. This has no unsaturations, so we don't have to worry about any of those. Okay, let's go through and assign fragments to each peak. And this particular spectrum only goes from 0 to 3 parts per million. So we're in a pretty small range here. So let's say we have a CH2, a CH2, CH2, and a CH3. We've taken care of all 9 hydrogen, but we've written down 4 carbon fragments in the formula. The problem is we only have 3 carbons to work with, and we still have a nitrogen to deal with. So instead of being a carbon, one of these groups is probably a nitrogen. Well, nitrogen, like oxygen, typically you don't see splitting through that peak. So this broad singlet here, that is most likely your nitrogen group. So instead of CH2, let's make that an NH2. Okay, now as far as connecting things together, let's take a look at the splitting here. This is a sextet. So sextet n plus 1 equals 6. N equals 5. So that means this carbon is connected to carbons with a total of 5 hydrogen. Well, how can we do that? Well, if we connect it to the CH3, there's 3. If we connect it to the CH2, There's 3 plus 2, 5. That gives us the right splitting for that particular signal. Well, we've taken care of the CH3. The CH2 has its 2 bonds, but this CH2 needs one more bond, as does the NH2. Well, let's just connect those two together. And that also explains why this signal is shifted downfield just a little bit, because it's bonded to the nitrogen. This CH2 is a triplet because it's connected to a carbon with 2 hydrogen. This CH3 is a triplet because it's connected to a carbon with 2 hydrogen. So we have everything connected. So this is just the propylamine. In this example, we're given the molecular formula C10H12O2, the proton NMR, and also some IR data. So from the molecular formula, you can find that there's 5 unsaturations. Now, you should be able to figure out the structure without the IR data, but in this case, since we have it, it's kind of useful. And since you have looked a little bit at IR in lab, you should be somewhat familiar. Stretch around 1720, that is in the C double bond O region. The 1610, 1505 stretches, those are a couple of stretches that tend to indicate an aromatic ring. Stretch around 1210, that is an sp2 hybridized carbon oxygen bond stretch, and 1010 is an sp3 hybridized carbon oxygen bond stretch. So when you see these 3 things together, what that often indicates is an ester. Because we have our C double bond O stretch, our sp2 carbon oxygen stretch, and then as long as this R group is sp3, we have our sp3 carbon oxygen stretch. So now, using this information, that will help us with the structure, but again, we probably could have gotten there without the IR data. First thing we're going to look at is we have all of this stuff in the arene region. Well, the main thing is 2, 4, 5 hydrogen in the aromatic region. That indicates a mono-substituted benzene ring. Now, due to the other stuff that's attached, and we'll see what that is in just a bit, it actually caused these different signals to get well resolved and kind of separated out on the spectrum, as opposed to just a messy multiplet, which is what we usually see. Okay, we have that. We have a CH2, a CH2, and a CH3. So let's see what we've accounted for. We've accounted for 6, 7, 8, 9 carbons. But there's 10 in the formula. So that must mean we have a carbon with no hydrogen. There's number 10. We've accounted for all 12 hydrogen, and then we have 2 oxygens that aren't accounted for. So let's just write those oxygens down so we have those fragments listed out. The only other note I'm going to make here is this CH2 at about almost 4.5. I think it's connected to something electronegative. Okay. So we have 5 unsaturations. Well, we've accounted for 4 with the aromatic ring. So what we can do now is to get a 5th unsaturation, it seems reasonable that we could take the carbon with no hydrogen and an oxygen, use those to make our C double bond O. That gives us our 5th unsaturation. Now the reason I crossed these out is that way we don't use them twice. I'll still leave my note, no hydrogen. Okay, so let's use what we have and see if we can connect these together. So I'm going to start with this CH2 that is a sextet. Okay, there's 6 lines there, meaning it's connected to, take 1 away from that, so 6 minus 1 is 5, meaning it's connected to carbons with a total of 5 hydrogen. Well, that means we can easily connect the CH2 to the CH3 and this CH2. Okay, we have that connected. Now, you might want to connect this CH2 to the C double bond O. Okay, but if that's the case, this C double bond O is going to pull these hydrogens, that signal downfield, to maybe 2.5. But it's clear down at about 4.5. So rather than a carbonyl, it makes more sense to connect it to this oxygen. Okay, then this oxygen, well, you don't want to just connect it to the aromatic ring because you'll finish out your chain and you'll have left out the carbonyl. Well, that carbonyl carbon needs 2 bonds, so let's connect it to the oxygen, and then we'll connect that to the aromatic ring. And in doing these connections, we did get our ester. So let's draw this again. We have our aromatic ring, C double bond O, O, CH2, CH2, CH3. Okay, and one thing I will go ahead and point out here is when you have this C double bond O, the carbonyl, attached to an aromatic ring, that tends to give good resolution of the signals in that ring. It separates them out nicely as opposed to just having one messy multiplet. Okay, example 6, C3H7BRO. No unsaturations, so we don't have to worry about any rings or double bonds or triple bonds. Let's go through and assign some groups. We'll do a CH2, CH2, CH3. There's our 3 carbons, our 7 hydrogen. We still have a bromine and an oxygen. Okay, a couple of notes we'll make. This CH2 down here at 5.5, okay, well, it's not a double bond proton. Even though you're getting near that double bond region, we know there's no double bonds because there's no unsaturations. So this must just be connected to something electronegative and very electronegative, or a couple of electronegative things to pull it down that far. The CH2 at 3.5, it's not as far downfield as the one at 5.5, but there's still something probably electronegative attached to that. Okay, let's use this information and see what we can connect together. Well, the CH3 is a triplet, so it should be connected to something with 2 hydrogen. Right there. And that's why the CH2 is a quartet, because it's connected to the CH3. Now, remember, bromine wants to make 1 bond. Oxygen wants to make 2 bonds. So oxygen is a good atom to bridge things together. Versus bromine, if I were just to connect this to the bromine, I would terminate my chain and I'm stuck. Whereas oxygen, if I connect this CH2 to the oxygen, I can form another bond. And I'll connect that oxygen to this CH2, and this CH2 to the bromine. Now, hopefully you can see why this CH2 is clear down at 5.5, because it's connected to the oxygen and the electronegative bromine. So a double electronegative effect pulling it downfield. So this one we have bromine, CH2, O, CH2, CH3. And of course this CH2 is a singlet because there's no CH's attached. This one we have C9H20. No unsaturations. But what you should immediately notice is that we have integrations for 2 hydrogen and 3 hydrogen, so only 5 hydrogen accounted for in the spectrum, but 20 hydrogen in the molecule. So these signals must represent equivalent hydrogen. And what can we multiply each by to give us a total of 20? Well, that would be 4. If we do it by 4, we get our first signal representing 8 hydrogen, our second one representing 12 hydrogen. There's all 20. So what could this be? Well, this first signal at about 1.2 or 1.3, that being 8 hydrogen, well, it can't be anything like a CH8 or even 2 CH4s, doesn't make any sense. So what if it's four equivalent CH2 groups? And then what if the one that integrated for 3 hydrogen is 4 equivalent methyl groups? Well, there's all of our 20 hydrogen, but only 8 of our 9 carbons. So there must also be a carbon with no hydrogen attached. So what this actually ends up being, each of these are connected, and it's just 4 equivalent ethyl groups. And then those ethyl groups are all attached to this carbon. So then we get this tetraethyl methane. Okay, in example 8, C7H14O2, calculate your unsaturations first. Okay, we have one we need to deal with, so either a double bond or a ring. Okay, so let's look and see what we have here. First thing, we have this signal down around 11. Well, if we take a look at our chemical shift table, let's just put it right here. Okay, around 11, that's where we tend to have carboxylic acids. So let's draw that. And that takes care of that one hydrogen. Okay, then we have some stuff right around 2. Let's make these a couple of CH2 groups. And one thing you'll notice right here hovering around 2 is the allylic region. So it's not quite downfilled enough to be connected to an electronegative atom, but I would say it's allylic, meaning that CH2 is connected to a carbon with a double bond. Maybe a double bond C, or a double bond O. Those are allylic. Okay, and then down in the saturated region, we have a singlet integrating for 9 hydrogen. Well, that is likely just 3 methyl groups that are all equivalent. So let's see what we've accounted for. Well, with our carboxylic acid, that double bond O, that takes care of our one unsaturation. Also, the carboxylic acid takes care of our 2 oxygens. We've accounted for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogen. So that's good. Okay, if we accounted for all 7 carbons, here's 1, 2, 3, 4, 5, 6. So there must also be a carbon with no hydrogen, in addition to the carboxylic acid carbon that doesn't have any hydrogen on it that we've already counted. Okay, well, one of the things that you should kind of spot is 3 equivalent methyls. Those should immediately call out your attention to being a potential tert-butyl group. And a tert-butyl group is going to have a carbon with no hydrogen. So there's that. Okay, from there we have our CH2 that we marked as allylic, meaning it's next to a carbon double bond. Well, our only carbon double bond is our carboxylic acid, so we can make that connection. Now that CH2 is a triplet, meaning it should be connected to something with 2 hydrogen. Well, it has a CH2 next door. And then we can connect this CH2 to our carbon with no hydrogen, and now everything works. So let's draw our final structure. Here's our tert-butyl group at the end. Okay, number 9 can be a little bit tricky. But let's walk through it and see what we can figure out. First thing, as always, unsaturations. You should find that there's one unsaturation. Okay, next thing, let's go through and assign our fragments. CH2, CH2, CH2. 6 hydrogens, that could be 3 equivalent CH2s. More likely, 2 equivalent CH3s. Because if you had 3 equivalent CH2s, it would be unlikely it would show up as a singlet. Okay, we've accounted for 5 of the 6 carbons. So there must be a carbon with no hydrogen. We've accounted for all 12 hydrogen. The only thing that's left, we still have an oxygen that needs accounted for. The only note I'm going to make on this one is this CH2 at about 3.7. I think it's connected to something electronegative. Okay, now what makes this one a little bit tricky is you see the unsaturation and you immediately go trying to figure out what that could be and try to think, well, maybe it's a double bond. Okay, but remember, unsaturations can be double bonds or rings. So let's kind of work with that and see what we can connect together. Okay, first of all, I need the CH2 connected to something electronegative. My only option is this oxygen. Now an oxygen needs to make a second bond, but I don't have any other hydrogen signals indicating connection to something electronegative. So it's probably connected to this carbon that doesn't have any hydrogen, therefore you don't see its effect. Okay, the next thing I see is, depending on which direction you want to work, this CH2 is a nice triplet. That means it's connected to something with 1. So triplet is 3. Take 1 away from that is 2. So it's connected to something with 2 hydrogen. Well, that means it's probably connected to one of these CH2s. Okay, now maybe look at these CH3 groups. They're a singlet, meaning they're connected to something that doesn't have any hydrogen. Well, we only have one option. So, let's connect them to this carbon. Okay, so where do we still need to make bonds? This carbon still needs a bond. This CH2 still needs a bond. This CH2 still needs a bond. Well, if you were to connect these two up, you would leave out one of the CH2s. So why not connect those and connect that? And what we end up with is a ring. And that ring is our one unsaturation. So if we draw this a little better, we have a ring with an oxygen in it. It's a 5-membered ring. And on the carbon next to the oxygen, we have a couple of methyl groups. Okay, example 10, C6H10O2. First step, as always, get your unsaturations. There are 2 we have to take care of. Okay, you get some IR data. You could probably do this without it, but it's there to help you. So 3100 broad and strong. That's in the OH region, but actually being at a slightly lower wave number, that's more likely a carboxylic acid OH. 1730, that's a carbonyl region. 1650, that's a carbon-carbon double bond. Okay, so we'll keep that stuff in mind, but let's just work through our spectrum as usual. Okay, down here at about 11. What's in the 11 region, 11 to 12? That's your carboxylic acid. So that fits our IR data. Okay, next, down here at about 5.5, we have a CH. And I want to make a little note here. This is in the alkene region, the double bond region. So I think that CH is part of a double bond. Okay, next at about 2.5, I'll make a CH2. And I think this is allylic. Just like our last example, or 2 examples back. And then I have 2 singlets, each integrating for 3 hydrogen. So I have 2 methyl groups. Not equivalent though, because they each give their own distinct singlet. Okay, let's check our atom count. I have 1, 2, 3, 4, 5 carbons. I need 6. So there must be a carbon with no hydrogen. Okay, I have all 10 hydrogen accounted for, and my 2 oxygens accounted for in my carboxylic acid. Okay, well, considering I need 2 unsaturations, I have 1 unsaturation with the carboxylic acid, C double bond O. My other one I think is an alkene, because I have something in the alkene region. But an alkene has 2 carbons. So what I think I have, let's go ahead and do this, but I don't have a signal for any other CHs. So I'm going to use this carbon with no hydrogen as my other alkene carbon, just like that. And this gives me my other unsaturation. Okay, so let's see what else we can connect together. Well, I have this CH2 that is a doublet, and it's allylic. Well, if it's a doublet, it needs to be connected to something with just 1 hydrogen. Well, what's my option? I can connect it to this alkene carbon, and that turns that into a doublet and makes it allylic like it should be. Okay, the next thing I have these methyl groups that are singlets. If they're singlets, they're attached to a carbon with no hydrogen. So they must be attached to this alkene carbon. So let's draw our lines and attach those. Okay, well, what still doesn't have the right number of bonds? This CH2 needs 1 more bond. The carboxylic acid needs a bond. So, making a bit of a mess with our lines, but we'll connect that. Okay, so let's try to straighten this up a little bit. Here's our carboxylic acid. It's connected to the CH2. That's connected to the alkene carbon that has 1 hydrogen. And then here's our alkene carbon with no hydrogen, which has methyl groups attached. If it helps, we can label these signals. Do A, B, C, D, and E. There's A, B, C, and then these two, we're not sure which one's which. Oop. But one would be D and one would be E. Okay, let's just look quickly at a couple of situations that might arise if you have an alkene in the molecule. In this case, here is a terminal alkene where we have our double bond, the hydrogen on each side. They are distinct because this hydrogen is cis to the methyl group, this hydrogen's trans to the methyl group, so they are distinct. So they do give two distinct signals. When you have something like this, they tend to give fairly separate signals. So here would be one, giving rise to one signal in the double bond region. And here's the other, giving rise to another signal in the double bond region. These terminal alkenes, again, tend to give fairly sharp signals, and the splitting, if there is any splitting, it tends to be very, very small, which is what we see right here. So that's one way to spot a terminal alkene. On the other hand, if you have an internal alkene, which is what we have here, here on this internal alkene we have actually hydrogen on the two alkene carbons. They are distinct. But a lot of times with these internal alkenes, you don't get great separation, and you tend to just get a large multiplet. But that multiplet should integrate for both of the alkene hydrogen. So that's one way to distinguish the internal alkene from the terminal alkene.